Will that work? Yes, that will work. Oh yeah, good. All right, this is the one I said asked for today, and you're like, well, it's today now. So find equation. It says find equations of both lines through the point 2, -3 that are tangent to the parabola y equals x squared plus x. Yes. Okay. Cool. So, if you try to start to think about it, I mean, if I graph this parabola, let's be a little bit careful about how to graph this. Can anybody tell me any damn thing about this parabola? It opens upwards. Oh, good. Now let's drill into it even deeper. What else? Can somebody else tell me something more technical about it? Its name is Bob. What are the x-intercepts? 1. No. 0. How do you factor this? Yes, x plus 1, so you get 0 and -1. So where's the vertex? It's got to be in between. Good. So at -1/2, and what's -1/2 squared plus -1/2? Is everybody cool with what I'm doing? I didn't have to do the negative b over 2a. I know the intercept, so the vertex has got to be in the middle, symmetric, right? So if I plug a -1/2 in, I should see where the vertex is. It's got to be down here. So I get 1/4 minus 1/2 is -1/4. I like it. So let's see. There's 1. So here's -1/4. So about right there. So there's my parabola. And just for shits and giggles, what's when I plug a 1 in, I get 2, right? All right. So here's the parabola. Make that big. And then the point they're curious about is 2, -3. Let me see if I did this well enough now. They want to know. So obviously here would work, right? I never quite get this one. And there's going to be another one that's insane. That's like way up here. That's going to be. I don't know if you guys are with me, because this is going to keep going forever. And that's my problem. Now I remember why I could never get this to work. So there's visually it's neat. There's an obvious one. All right, I really want you to understand. I should not have drawn that. I really want you to understand what the point of the question is. Find the tangent lines. There are 2 of them. The lines that are tangent to the parabola and go through this point. Here's an obvious one. That's tangent to the parabola right there. So I got a good guess for where it is. And it goes through 2, -3. And there's another one that's going to happen up here. This is going to keep going forever. So somewhere up here, it's going to have the right slope to come back down and hit there. Or somewhere way up there. You guys see that? Is that cool? This parabola, of course, keeps going up forever. So there are 2 points. There won't always be 2 points. But this is one special case. Right? Okay? Maybe. So then the next thing is like, how the hell do I do that shit, Jeff? I don't know. So if I want to talk about tangent to this curve, what's a really good idea? What do I know I'm going to have to use at some point? Yeah, I know I'm going to need to do this derivative, which is what? Kick-ass. And just to give you the 2 other things you need. What point is this? Do I know for sure? I mean, based on the way I drew it, I can guess. But what point is it? I don't know. So what point is it?
-0.
We don't know. It could have been just the way I drew it. Did I draw it really well? I would say no. For me, it's really, really good. But in general, this is not good. This is not good enough just to make. So what point? What point is that? What point is this? What point is that? I don't know. So what point is it? Algebra. If you don't know what something is, you call it. Good. Now this is a point, so you call it xy. Good. All right. So this is the point xy. Do you understand what I'm trying to say? So you're past algebra, but the minute you're in algebra, if you don't know something, you pretend like you know it. That's really kind of the foundation of algebra. What is it? It's x. What? But if we pretend like we know what it is, we can then do shit with it, right? We call it x, and then I do shit with it. That's the whole idea of algebra. So this is the point that I don't know. So I got to call it xy. But what's y? If I know x is x, what's y?
Y.
No. I like that. That's good. Y is y.
Why is Y?
Because. What is y on this curve? What's the curve defined by? Thank you. Stephen over there's like. Listen to me, Jeff. You guys see now this idea is huge, believe it or not. This is really simple and dumb in a way, but this is huge to be able to write this. Any curve I give you, you can write a point on the curve as x comma f of x. I mean, that's almost like, well, of course I can, but then you can't do it in a problem like this. That's exactly what you need to do. Because now what's the slope between this point and that? What's the slope between those two? What point is this again? So what's the slope between that point and this point? That's easy. That's easy. And you're all like, shut up, Jeff. You're easy shit. Take that away. But come on now. It is easy. Come on. This xy, xy.
Yes.
What's the slope?
The y2 minus y1.
So one way to look at the slope is just to take it directly. What would be x squared plus x minus negative 3, right? Over x minus 2. Is that cool? You guys with me? y2 minus y1 over x2 minus x1. Snap is right. So what the focus of this problem is to use, bless you, the two different ways we have of looking at slope. One way is algebra. The second way is calculus. So what do I want to be true? I want this slope, come on, to equal that slope. I need them to be equal to each other. All right, maybe there's opening some doors. I mean, there's a lot in this problem that actually carries over to other problems. Being able to write the general point on a curve. When you see it, it's like, well, duh. But people forget this. This is going to come in handy a lot of times. This is how you write the general point on some curve is x comma f of x. Unless you have a three-dimensional curve, and that would be something else. Well, let's stick with two dimensions. Two meaning a plane. That's what I meant. 10. You guys understand how to go from there? Because now I get the slope. I know this is the slope, and I know that's the slope. So it's set to equal to each other. And solve. You're trying to figure out, what are you trying to figure out? Where the x point that will make the slope of this match the slope of a line going through this point. Do you understand? That's what I'm doing. What's the slope of a line going through that point and anywhere in this parabola? This. What's the slope at any point in the parabola? That. So if I force them to be equal to each other, I will find the point or points that have this right slope to go through that point. That's the whole idea. Maybe. So that one's not an easy problem. I don't want you to feel bad. I don't mean to make you feel bad if you didn't see how to do some of this. That's why I love this problem, and that's why I don't have any problems doing part of it for you, because it's weird until you first see it. Yes?
Will that like give you an x and then you plug the x back in?
In fact, it'll give you two x's, which is why they say, two lines. Yes?
So if we just do 2x plus 1 equals x squared plus...
Yes, exactly. I like it.
Can we simplify that down, right?
Can you? I wouldn't try. It'd be much easier to multiply it up and then get it over, make it a quadratic, see if you can factor it, blah, 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 blah. Right? You should be able to attack this bad boy now, no problem. I mean, you've done this ever since algebra. What have you had? The width, the length is 1 less than twice the width. Remember this shit here? Alright, so one way of looking at the perimeter would have been 6x minus 2. That's one way to look at the perimeter, right? And then what if I said I had 80 feet of fencing and I want to use all of it? So another way of looking at the perimeter would be I want it to be 80. So you set them equal to each other and you see where they agree. I mean, it's exactly what we're doing here, just at a higher level. But I really want you to see that's exactly what you did in algebra. You looked at something in two different ways and you set them equal to each other. That's what we're doing here. Look at slope this way, look at slope that way, force them to be equal to each other. Maybe. Alright, that's enough like And then part B, you should be able to figure that out. There's certainly an area that if you put the point, instead of here, you put the point somewhere else, you won't find any tangent lines. You should be able to figure that out. Anything else from homework? Yes.
75?
In the same section?
Yeah.
Oh, okay. So here's the thing here's the quick way to get a handle on differentiability. For a function to be differentiable at a point, the slopes from both directions must agree at that point. So for example, is absolute value differentiable at 0?
No.
Why?
Because it's not.
Slope here is
Right.
-1, and the slope here is +1. So whatever. I'm thinking about this like it's just absolute value x. So it's 1 and -1. The slopes don't agree, therefore it's not differentiable. So it feels sort of like continuous in a way, right? You with me? And it is very similar. It's almost the same thing. And that's why they talk about a cusp not being differentiable. That's why the slopes don't agree. And like I said, you don't want to be in that plane. When your slope changes an incredible amount very quickly, you're dead, right? Sorry. What was the point? Okay, so all you got to do there is it's going to feel a lot like the continuous section. You want to make the slope from one side of 2 match up with the slope from the other side of 2. That's all you got to do, right? That's all I'm going to say on that. And that's number 75 in section 3.1. I'm hopeful. That should feel very familiar. Okay, cool. Anything else from homework?
71?
Do it again.
71?
Let's see what's left in this section. All right. So I would hope that doing number 60 might. Do you see number 71 how it matches with number 60 in a way? I want the equation of the tangent line to be 3x minus 2, right? Which means I want the slope of the tangent to be, if I want the tangent line to be 3x minus 2, I want the slope of the tangent to be, come on now. 3. Thank you. Everybody else is on. Well, I like that you all waited. But you with me? It's exactly like number 60 in a way, because they give me the result, and I know that what I want the slope to be, so then I take the slope and I force it to equal that. Yeah. That's why I signed that problem. It's very similar to 60 about take the derivative and then force it to equal something, because you know you want it to equal something. Right? There's a little bit more after that, but that's the first step. Okay. Maybe. Okay. All right. Anything else? Did I miss anybody? All right, that's plenty. Let's get back into 3.2. We do have to finish up quotient rule. Oh, and I do need to talk about e to the x kind of stuff. So let me start with e to the x stuff here real quick. So let's just say it's a to the x. And how would I find this derivative by the... Since I don't know what it is, what must I use?
Definition of derivative.
Beautiful, which just says what?
Which goes to 0.
H goes to 0. F of x plus h, f of x over h. Come on, x. So what would this look like for this function? It would be limit h goes to 0.
A to the x plus h.
A to the x plus h minus a to the x over h. Now here's another thing that people forget. How can I rewrite a to the x plus h? When do I add powers? When I was multiplying, so I can break it back apart. To be what? Beautiful. See that? It's real easy to forget. Math goes both ways, right? Think what you will of it. Now what's screaming out to you at the top there? Something should be screaming to be
Factor
done.
out a to the
Yeah, factor out a to the x. So then you get left with a to the h minus 1 over h. Is this depend on h at all? Does that depend on h?
No.
No, so I can effectively take it out, or the limit of this is just going to be itself, because it doesn't give a shit about h, right? As h goes to 0, what does a to the x do? Sits there. That's nice, you're small. So really, the whole thing boils down to analyzing this. Oh, and instead of just trotting out all kinds of weird shit at you, basically, there are ways to analyze this. There are easier ways to do it once we learn some more derivative rules, and there are easier things to look at beyond this. But if you really study this and you start making table of values, letting h get really, really close to 0, let a computer crunch it, let h get even closer to 0 than a human ever could, right? You'll start to realize that. And what would be really interesting here? Let me not jump the gun a little bit. What would be really interesting here is if I let this go to 1. If I said, what would make this become 1? What would make that limit become 1? That's what would be really interesting, because then what would that say? The derivative of a to the x would be a to the x. That would be really interesting, right? Maybe. So what happens to make this equal 1, a has to be e. And that's one of its definitions, actually. I don't know, you don't know too much about e. You probably know e. You know e. But I'm willing to bet that you don't know much about e. You just know it's there. Hopefully you know more about pi. What's pi?
The ratio.
Diameter and the circumference.
Cool. Circumference over diameter. So no matter what the circle is. So that was special. So that's where pi came from. I have to take the circumference divided by diameter. I always got the same number. All these cultures had different estimations for it. They thought it came from God because, hey, what the hell, man? Make a big-ass circle, make a tiny-ass circle, and it still comes out to be the same ratio. It's freaky as hell. So that's why they gave it its own letter. You guys are kind of with me a little bit. So this E comes up. This is just one more place E comes up. E pops. So that number keeps coming up, and so they wanted to give it its own letter. And Euler actually gave it the letter E, not because his first name starts with E or his last name is E, his first letter is E, not because, it was just because that was the next letter he was going to use for a variable he got. So he wasn't that obnoxious. So what the hell does all this shit mean? And real quick, if A is not E, so to make this 1, A must be E. If A is 2, this limit comes out to be ln of 2. If A is 3, this limit comes out to be ln of 3. So in general, this limit is ln of A. So let me summarize what we just figured out, or what you just watched happen, I guess. Right? Because it's too weird to try to do on our own. We just figured this out. We figured out if I have f of x equal e to the x, f prime will be e to the x.
Yeah.
That kicks ass. Let that kick ass. That's awesome. In general, if I have a to the x, f prime will be a to the x times natural log of the base. Which now you look back and you're like, well, what if a was e? What's ln of e? 1. So it kind of comes back and so hey, it's the only base. The ln is 1. So bam, there it is. I know. And if you really want to get mind blown, you can look at the history of this. Not until you get to 280 can you come back. We don't teach this in the order that it was discovered. I really want you to understand. If you take 280 and you get to sequences in series, whoever your teacher is, ask them if they know some backwards derivative proofs or something. That's where derivatives were actually proven, was when you learn 280 shit. That came before all this. A lot of this shit did. It's just that we said, well, it's easier to teach it this way. We'll teach it this way. So if you're going to take 280, you'll see. If you won't take 280, too bad. It's your forever cliffhanger. It's too bad. So sad. All right. You've chosen. Okay. So that's huge. That's nice. So real quick, if I had g of x equals 3 to the x, what would g prime be? 3 to the x. ln3. So I always think of that as an adjustment. If it's not e, it needs to be adjusted so it matches back up correctly. If it is e, it don't need no adjusting. It's fine. I don't know if you want to think of it that way, but I won't. Cool. Josh, you alright? That was a lot.
Okay, no. Okay, so like 3.1 was all about bringing the x down and then like pushing.
No. Never.
Okay.
I'm sorry, Josh. So we know a rule for if the variable is, what's the power rule if the variable is where? In the base. And the power is a constant. This is fundamentally a different function. It's like comparing tangent to the square root, the fourth root of something, and saying, why don't they act the same? Of course they don't act the same. They're nowhere near the same. So these are so desperately nowhere near. X cubed and 3 to the x are nowhere near the same. Cool? Except at 3, right? Then they both agree. That's the one time in how many possibilities, an infinite number that they agree. So I'd say that they're not the same at all. Are you guys kind of with me? So it's a good point. I know the power rule. This rule here is awesome. Actually, it doesn't even turn out to be as nice as this one. But this rule kicks ass because it's relatively simple, right? No matter how ugly the power gets, it's easy to subtract 1 from ooh. You with me? But do you understand? I should not expect two completely different functions to operate anywhere near the same way because they're different. This is so desperately different from that. The variable is in the power here. That is freaky as shit. If you really think about it, I mean, that's just freaky to let the power be the thing that changes. Okay, shit, all right. So I really want you to understand, what would this picture look like? Well, it would look like parabola or cubic or some, the butt graph, whatever. Right? You with me? That's polynomials. They're polynomial. This guy always looks like that, which kind of explains why its slope is so easy to calculate. Kind of with me? The derivative rule for this is really, really easy. This is easy, but sometimes the calculations get funky. This one can't really get funky at all. Because the graph is just always the same, basically, right? Do you start to see what I'm saying? They are so desperately not the same category of function, so why would the derivatives look anywhere near the same? But I like what you're saying because I always get somebody who says the derivative of this equals this. Right? Don't write that down. I see people writing it down. Don't write that down. And then say to a tutor, my teacher said this. Does he feel all right? No. If you write it down, put a big X through it and say no. That's not good because that's not in the form to follow that rule.
So you have to know the exponent for that one.
You have to know the exponent has to be a constant, or in this case, n means a constant number, right? It's not a variable.
Constant, then you can't use that, or you don't know.
If the power is a variable, then you can't use this rule.
Okay. All right.
So we are going to get to the point where we can talk about this function. You ready? I don't know if you're ready.
Whoa.
This function. Right? What? We will do that guy's derivative before this class is, not today, but before the semester's over. In fact, before we're out of this chapter. Alright, well, don't worry about that yet. That is really funky. That was on my junior year proficiency exam. I remember that. They just, out of nowhere, they said, what do you think about this function? Oh, shit, holy shit, no freaking... Alright, sorry. Alright, how do we feel so far about this? So these are now rules that we just know. In fact, that is the general rule, and that is a special case, of course, right? So one time where L and V would just be 1. Okay, so what did we learn yesterday? Or what did we talk about? And we're learning now. Product rule. We haven't done quotient rule yet officially. So if I have a function times another function, how would I do its derivative? Yes. So they each get a term, right? So now it's F turn, and now it's G's turn. So they each get a term. I like it. Let's do a quick example, 2 different ways, just to kind of validate for ourselves that this looks right. It's not going to be a proof. We proved it yesterday. But let's say I had, what you got, Jeff? Hello, man. X plus 1 times 2x minus 3, sure. Let's apply product rule first, and then we'll do it the way that you should immediately want to do it, which is just to multiply this damn thing out, right? So there are some problems in this section where it's like this, and polynomials are not good examples of product rule. Until we learn chain rule, you won't see the full power of product rule. When we learn chain rule, we'll be able to do this kind of problem. Do you understand? X plus 1 to the 111th power. Do you want to multiply that one out?
Probably not.
I don't know. Even if you know Pascal's triangle, you're like, I don't have enough paper to go out there for. Screw that. So when we learn chain rule combined with product rule, that's powerful. That's like, product rule right now by itself is kind of lame, a little bit lame, right? But if I apply product rule, what's it going to look like? So here's let me call this y. So what's y prime going to be? And I'm desperately going to try to get you guys to do this. Write the rule, then do derivatives. What do I mean by that? What's the rule say?
Oh, write it out.
Take this guy's derivative, leave this guy alone. Plus. Yeah, leave this guy alone. Derivative of 2x minus 3. I like it. You've got to trust me on this, even if you don't. Do it anyway. I'm not going to take points off if you don't, but the people that don't are the people that are going to make easy mistakes. Because if you try to do derivative rules and derivatives at the same time, you lose things. Especially when we get to chain rule. And some of you guys are like, you keep saying chain rule, what the hell is that? So now I do the derivative. What's the derivative of this? 1. Cool. So 1 times this. That's great. And then what's the derivative of 2x minus 3? 2. So I end up with 2x plus 2x is 4x, minus 3 plus 2 is minus 1. Is that cool? Yeah. Come on, now you guys can distribute blah, blah, blah. Don't let me write all that crap down. All right, cool. Now what do you get if you first simplify instead? Well, what does y become if you first simplify? What do you get? Who to what?
2x squared.
2x squared. Yeah, plus 2 minus 3 is minus 1, minus 3. Is that cool? Yes, it is cool. I'm not even going to ask you. Okay. Y prime then is?
4x minus 1.
I like it. So you see how that obviously was much easier, right? So on one hand, if I had nothing but polynomials in here, I would like to just multiply the damn things out. Product rule doesn't really help me. You with me? This is not a proof, but if we didn't get the same things here, that would be a bad sign. Right? Thank God we got the same things. Okay, so it's not a counterexample. I haven't disproven it yet. How do you feel so far? You okay? All right. So let's. Okay. Everybody got this here? What's the matter? You didn't have it? I'm sorry.
I got it.
You got it. All right. I always have to have one person that messes with me when I say it. Wait! Oh, shit. Just to show you an example where it really does help. I can't remember. Do I have... Oh, yeah, I do have trig functions. Oh, we got to know that, too. If I had something like this here... So you have the option, but no matter what you do, you can't escape product rule this time, right? If you distribute, you still have a product rule and a product rule. The first thing I should do probably is what?
Write the rule.
No, even better than that.
You write it fractional.
Yeah, good. Write it in the right form for the rule in there that I need, right? Oh, it so desperately sucks if you make a mistake here, but I give you partial credit, but come on. 4's on the bottom, right roots, bottom. And now if I apply the rule says derivative of this times that plus
EX.
good. And then this guy gets a turn. Yeah, there's Jeff. So this one I'll do. So helpful. And what happens over there?
3x squared
Good, 3x squared.
minus 3/4. Negative 1/4.
Good, 3 minus 4 is negative 1 over 4. Sweet. You guys with me? Is that cool? And see, if you write the rule, it'll make the rule solidify in your brain more. Plus, the next step is just find your primes and attack that. Find the prime, attack it, and rewrite everything else. It makes the problem much easier to keep track of. If you don't believe me, fine. Go make your mistakes. Now, is there really any purpose? Do you guys see how, would there be any like terms if I distributed the e to the x? Do you guys see that? Would there be any like terms? Is there another x cubed in there somewhere? X squared? No. So really what I would rather do is just pull e to the x out of the whole damn thing. That's the only thing that would really be at all useful. Some of you guys might even do weird shit with that if you want to.
So,
I don't care.
do you want us to leave it like how the top one is, or the bottom?
On this problem, it really doesn't matter. If you stop here, I'm fine with that.
Okay.
But if there's any like terms, any regular little simplification that you don't do, you might lose points. You need to simplify. There is here, it's almost, who cares which way it looks? There's no really big advantage either way. How are we doing so far? Yes, sir.
What's e to the x times e to the x?
Oh yeah, all right. What's the rule when you multiply like bases?
Yeah, I have to explain.
Yeah, so it'll be e to the 2x. Good question, because that freaks people out too. But it's going to come up later, because we actually right now don't have a clue how to, well, we don't know how to do this derivative directly,